The loudest sound on a basketball court is actually the sound of physics failing and resetting thousands of times every single second. Why do basketball shoes squeak? And how does that high-pitched scream reveal a hidden law of motion that governs everything from violin music to the destructive power of earthquakes? In the next several minutes, we will answer that question by looking at the invisible mechanical struggle happening between rubber and wood. You will understand how a simple sneaker becomes a scientific instrument that measures the exact moment a solid surface turns into a vibrating wave. Before we finish, you will see why that annoying noise is actually a physical signal that the floor and the shoe are no longer moving as one. We often think of friction as a steady force, like a constant wind blowing against a car, but the squeak proves this is a lie. When you watch a player make a hard cut, you are seeing a process called stick-slip motion, where the shoe is not actually sliding at all. It is catching, stretching, snapping forward, and catching again in a cycle so fast that your eyes cannot track it.
The proof of this hidden mechanism is found in the frequency of the sound itself, which usually rings out between 1,000 and 3,000 hertz. This specific range is where human ears are most sensitive, meaning the shoe is effectively shouting a warning that it has reached the absolute limit of its grip. This is not a simple scrape. It is a violent transition between two different states of physical reality that researchers are only now beginning to fully map out. To understand why this happens, we have to look at the default story we are usually told about how things move. Most people assume that when you drag an object across a floor, it either stays put or it slides smoothly. We are taught that friction is just a number, a constant resistance that pushes back against us. But if friction were truly a constant force, a basketball shoe would be silent. It would either grip the floor perfectly, or it would slide with a low, dull hiss. The sharp, piercing squeak is a contradiction because it represents a vibration, and vibration requires a rapid change in force. Scientists have long dismissed these sounds as trivial side effects of movement, yet the squeak is actually a failure of the standard model of friction. It tells us that the interface between two surfaces is not a steady state, but a chaotic battleground of energy being stored and released. This mismatch between the smooth slide we expect and the jagged sound we hear is the first clue that something much deeper is happening at the microscopic level. When a player plants their foot, the rubber does not just sit there. It bonds to the floor at an atomic level. This creates a state of static friction that is much stronger than the friction of a moving object. The squeak begins at the exact moment this bond breaks, and the shoe is forced to transition from standing still to moving fast. Imagine the sole of a basketball shoe not as a solid slab of rubber, but as a forest of millions of tiny, flexible pillars. When a player tries to stop, these microscopic ridges do not just slide, they bend. They grip the microscopic imperfections in the hardwood floor and stretch like tiny rubber bands. This is the stick phase of the cycle. During this brief moment, the shoe is actually storing potential energy, much like a bow being drawn back before an arrow is fired. The reason we do not see this with our naked eyes is that the scale of the movement is too small and the speed is too high. However, high-speed cameras and laser measurements show that the material is deforming under extreme stress. The tension builds up until it exceeds the maximum grip of the rubber. At that precise millisecond, the bond snaps. The material cannot hold on any longer, and it recoils forward. This is the slip phase, where the rubber actually moves faster than the leg that is pulling it.
This rapid snapback releases all that stored energy into the air as a pulse of sound. Because this happens thousands of times per second, those individual pulses of sound blend together into the continuous squeak we recognize from the television. This cycle is almost identical to the physics of a violin. When a musician draws a bow across a string, the bow does not glide smoothly. Instead, the rosin on the bow causes it to stick to the string, pulling it sideways until the tension is too great. The string then snaps back to its original position, only to be caught by the bow again instantly. This creates a sustained vibration that we hear as a musical note. In this sense, a basketball court is a giant instrument, and the player is the musician. The rubber sole acts as the bow, and the hardwood floor acts as the string. The reason the sound is so high-pitched is due to the stiffness of the rubber. Harder rubber creates a faster snap and a higher frequency, while softer rubber might create a lower groan or no sound at all. This comparison helps us understand that the squeak is not just noise. It is a resonance. It is a physical signature of the materials involved and the pressure being applied. If the friction did not drop sharply the moment the movement started, the vibration could never begin. This drop is known as the static to kinetic transition, and the squeak is the literal sound of that cliff edge in physics. One of the most fascinating ways researchers have studied this is through the use of transparent glass floors. By replacing the hardwood with thick, clear glass and using a technique called total internal reflection, scientists can see exactly where the shoe touches the surface. When a shoe is pressed against the glass, the points of contact light up. As the shoe begins to squeak, these contact patches do not just slide, they flicker and dance. They appear to vanish and reappear in a rhythmic pattern. This proves that the shoe is not in constant contact with the floor during a squeak. Instead, it is hopping across the surface at a microscopic scale. These are sometimes called detachment waves or Shalamach waves. These waves ripple across the contact zone of the sole, with each wave releasing a specific pulse of energy. The sight of these flashes of light confirms that the friction is not uniform. It is a series of tiny explosions of movement. Every time a contact patch breaks and resets, it sends a shock wave through the rest of the shoe, reinforcing the vibration and making the sound louder. This visual evidence destroys the idea of a smooth slide and replaces it with a picture of a surface that is constantly tearing itself away from the ground. This same mechanical instability is what causes earthquakes. On a much larger scale, tectonic plates are like the shoe and the floor. They are pushed together by massive forces, but they do not slide past each other smoothly because of the friction between the rocks. Instead, they stick. They stay stuck for decades or centuries, bending and warping the crust of the earth as they store incredible amounts of potential energy. Eventually, the stress becomes too much and the plates slip in a sudden, violent snap. That snap is the earthquake, and the seismic waves it sends through the ground are the low-frequency version of a basketball shoe squeak. The physics is exactly the same, a stick-slip cycle governed by the rate and state of the friction. By studying the way a shoe behaves on a court, scientists can actually build better mathematical models for how faults in the earth might fail. The shoe provides a controlled environment to measure how speed, pressure, and material properties change the way a surface slips. It turns a massive, unpredictable natural disaster into a repeatable laboratory experiment that fits in the palm of your hand. One of the key variables in this process is something called the negative slope instability. In most simple physics problems, we assume that friction stays the same regardless of how fast you are moving. But in the real world, friction often decreases as velocity increases.
This creates a dangerous feedback loop. If a small slip occurs, the friction drops, which makes the slip happen even faster, which causes the friction to drop even more. This instability is what allows a tiny vibration to grow into a loud, screaming squeak. If the friction increased with speed, any vibration would be instantly dampened out and the shoe would be silent. The squeak is therefore a physical proof of this negative slope. It tells us that the rubber is losing its grip the faster it moves. This is why a squeak can be a warning sign for a player. It indicates that they are on the verge of a total loss of traction. If the stick phase becomes too short and the slip phase becomes too long, the player will simply slide out and fall.
The sound is a signal that the interface is currently unstable, and that the limits of the material have been reached. Interestingly, the environment of the court changes this physics significantly. For example, dust is the enemy of the squeak. Most people think dust makes a floor slippery because it acts like tiny ball bearings, and that is partially true. But more importantly, dust prevents the stick phase from ever happening. The dust particles fill the microscopic gaps in the wood and the rubber, preventing the atoms from bonding together. Without that initial bond, the rubber cannot stretch and store energy. It just glides over the dust. This is why a dusty floor is silently slippery. The absence of a squeak is often more dangerous for a basketball player than the presence of one. A loud squeak means the shoe is still catching the floor and releasing energy. A silent slide means there is no catching at all. This is why you see players constantly wiping the bottoms of their shoes with their hands. They are removing the dust to restore the high friction contact that allows the stick-slip cycle to occur. They are literally cleaning their shoes to make them louder, because volume is a proxy for grip. Moisture also plays a strange role in this mechanical drama. A tiny amount of sweat or water can actually increase the intensity of a squeak. This is because a thin film of liquid can act as a temporary adhesive through capillary action, making the stick phase even stronger. The rubber bonds even more tightly to the floor, allowing more energy to be stored before the snap. When the slip finally happens, it is more violent and the sound is louder. However, if there's too much moisture, the liquid starts to act as a lubricant, and the friction drops to almost zero. The shoe then enters a hydroplaning state, where it never sticks at all. This delicate balance between dry, damp, and wet surfaces shows how sensitive the stick-slip mechanism is to the exact conditions of the contact zone. Even a change in the humidity of the gym can change the pitch and volume of the shoes. The squeak is a real-time sensor for the chemical and physical state of the floor. We also have to consider the design of the shoe itself. The herringbone patterns and grooves on the bottom of a basketball shoe are not just for show. They are engineered to manage the stick-slip process. These grooves create small, independent zones of rubber that can each go through their own stick-slip cycles at different times. Instead of the whole foot slipping, at once, the slip travels as a wave across the sole. This prevents a catastrophic loss of traction. Furthermore, these grooves act as miniature resonance chambers. They can trap air and sound waves, amplifying the frequency of the squeak. This is why different brands and models of shoes have distinct sounds. A shoe with deep, wide grooves will have a different acoustic signature than a shoe with a flat, solid sole. The engineering of the tread is essentially the engineering of the vibration. High-performance shoes are designed to maximize the stick phase, while ensuring that the slip phase is as short and controlled as possible. At the most extreme level, the energy involved in a squeak is enough to cause physical changes to the molecules of the shoe. During the tiny millisecond of the slip, the friction generates intense heat at the contact points. Even though the rest of the shoe stays cool, the very tips of the rubber ridges can experience brief heat spikes. This can be enough to tear individual molecules away from the sole, leaving behind an invisible trail of chemical rubber on the court. If you have ever seen dark scuff marks on a gym floor, you are seeing the aftermath of a massive stick slip event, where the energy was so high that the material itself failed. The squeak is the acoustic byproduct of this material destruction. It is the sound of bonds breaking, not just between the shoe and the floor, but within the rubber itself. This adds a layer of reverence to the sound. It is the scream of a material being pushed to its breaking point to keep a human being from falling over. So, what does all of this evidence tell us about the title question? Why do basketball shoes squeak? And what does it reveal about physics? The answer is that the squeak is the audible manifestation of the stick-slip cycle, a fundamental process where steady force is converted into rapid vibration. The evidence eliminates the old idea that friction is a constant, smooth drag. Instead, it proves that friction is a series of high-speed arrests and releases. The measurement of the sound frequency and the visual evidence from glass floors show that the shoe is actually jumping and snapping across the surface, not sliding. This mechanism remains the strongest explanation for why we hear a high-pitched tone instead of a dull roar. While the basic rules of stick slip are understood, the exact way that different rubber compounds interact at the atomic level is still a field of active research. We still cannot perfectly predict when a surface will transition from a stable stick to an unstable slip, which is why earthquakes remain so hard to forecast. This verdict changes how we should look at the world around us. The squeak of a shoe is no longer just a background noise in a sports game. It is a laboratory demonstration of the same forces that shape mountains and create music. It is a reminder that the world is much more dynamic and unstable than it appears to the naked eye. When you hear that sound, you are hearing the physics of instability. You are hearing the moment where the static world breaks and the kinetic world takes over. It is a signal of maximum performance and a warning of imminent failure. The next time you are on a court or watching a game, listen to the shoes. They are telling you exactly how much energy is being fought over at the microscopic level. They are proof that even the most common, everyday objects are governed by complex, beautiful, and sometimes violent laws of motion. This forensic look at a simple sound reveals a hidden layer of reality that is always there, vibrating just beneath our feet. If you found this deep dive into the physics of everyday life interesting, consider following the channel for more explorations into the hidden mechanisms of our world.